having learned about discovering that atoms existed, now we're going to get into what the structure of an atom actually looks like. Okay? So, we know Dalton was incorrect about them not being able to be broken down. So now, instead of defining elements as things that can't be broken down, we have a new term. We have atom, and we define it as the smallest particle of an element that retains the chemical properties of that element. So a single atom of a metal would still be conductive of electricity, but if you break that atom down into protons, neutrons, and electrons, those don't necessarily conduct electricity the way that that metal would have. So once you break it down further than this, you start to lose the characteristics of the element that that atom is from. The following experiments, we're going to learn about a lot of different experiments today, formed the foundation of our understanding of the structure of an atom. Okay. We're going to start with cathode ray tube experiments. So in the 1800s, there were a whole bunch of people doing these experiments, and what they did was they took an electric current and they ran it through a gas at very low pressure. So gases normally at normal atmospheric pressure don't really conduct electricity. So in order to get the electricity to be conducted through it, they had to put it at very, very low pressures. So what they did is they took a glass tube and they essentially sucked a lot of air out of it, created a vacuum, so it was very low pressure. Okay? They were carried out in these glass tubes hooked up to vacuum pumps, which they called cathode ray tubes. This is what they looked like, okay? So you had a glass tube, and then you had this section down here where the vacuum was attached, and then up here we have the cathode, okay? And then over here we have the anode, okay? So they had these glass tubes, air that was at very low pressure, and then they would put different gases in. So sometimes they might have used oxygen, sometimes they might have used helium. They just used different gases to be the air inside these tubes. The experimenters noticed a couple of things. They noticed first that when they passed electricity through these cathode ray tubes, directly opposite of the cathode, so that spot we noticed on there, that the tube would glow a little bit. There'd be a faint glow. They hypothesized that this glow was caused by a stream of particles, and they didn't have a name for those particles, so they called them a cathode ray. And they said when that flowed from the cathode to the anode, electricity was passed, and that's why it was glowing. Testing their hypothesis, because they wanted to test it to see if they were correct about there being a particle there causing this, they got the following results. First, they noticed that cathode rays were deflected by a magnetic field. Deflected means that they were caused to move away from it. Okay? So a wire that carries an electric current that is known to have a negative charge would react in a very similar way to a magnetic field. And they noticed that those rays were deflected away from any object that was negatively charged, placed near this tube. So, they came up with this new hypothesis based on this. They said cathode rays must be negatively charged, because we know that negative objects repel negative objects. So if you passed a negative object by another negative object, it's going to be deflected. It's going to be moved away from it. So if they're deflected by a magnetic field, which would deflect a negative wire, they must be negative. And if they're deflected by a negatively charged object, that would support the hypothesis that they are negatively charged. Okay, so now they have this idea that cathode rays are negatively charged. Now we need to test that. So, a man named Joseph John Thomson ran a series of experiments to support, which the evidence from them wound up supporting the hypothesis that cathode rays were negatively charged. And during those experiments, he was able to measure the ratio of the charge of a cathode ray compared to its mass. So he wasn't actually able to measure the mass or measure the charge, but he was able to measure the ratio between them. Okay? So this was always the same regardless of what gas was used in the cathode ray. This might sound like an insignificant thing, but this is actually very important because the conclusion that he came to was that all cathode rays must be made of the same particles. Because if that charge to mass ratio is always the same, no matter what element we pick, and we know elements have different masses, but if that charge to mass ratio is always the same, then whatever these rays are made of needs to be the same every time. So it must be a particle that exists in all of these elements that is the same, that's making these cathode rays. And he named them electrons. So we now know that what these scientists thought was a cathode ray, that's what they were calling it, passing through here, is actually the electrons in the gas. Next, a man named Robert A. Millikan gets involved. While Thomson's experiment revealed that electrons have a very large charge-to-mass ratio, meaning they have a large charge and their mass is very small, he was unable to actually measure it. Millikan, on the other hand, was able to actually measure the charge on a single electron. And as a result, using that charge and the charge-to-mass ratio, the scientists were then able to calculate the mass of the electron. Okay? Now, they were very close. They were just a little bit off. But now we know that the mass of an electron is about 1/2000th the mass of the simplest hydrogen atom. It's about 9.109 times 10 to the negative 31 kilograms. So it's a very, very small piece of matter. It does not have a lot of mass. So now we have a couple new theories emerging, okay? Because we've just gotten this, what was for them probably world-shattering evidence that that elements are not, strictly speaking, indivisible, right? An atom can be broken down. So now we have two new hypotheses. One, because atoms are electrically neutral, there must contain some positive charge to balance the negative charge of the electron. Okay, so there's got to be other pieces, they're saying. We know atoms usually don't have a charge on them. So if there's an electric charge in there that's negative, then there also has to be a positive one. Otherwise, they would be charged all the time. And secondly, we discovered that electrons have such little mass, and we know the masses of atoms of specific elements, they must contain other particles, because otherwise, where is all that mass coming from? There has to be something else in there. So, check for understanding. Why was it necessary to use experiments like the ones that J.J. Thomson and Robert A. Miller performed to infer information about electrons? Why do we need to run these experiments in order to get information about them? Okay, you're going to take 30 seconds to jot down your answer, and then you're going to share it with your partner. So what are we thinking? Why do we have to run these experiments?
Support and back up the hypothesis of them.
Right, to support and back up the hypothesis, right? And is it possible for us to observe electrons? No, they're tiny, right? We just learned that their mass is like a 2,000th of a kilogram. Like it's very small, okay? So we can't see them with our eyes. So it's necessary to run these experiments because that's the only way we have of getting information about them. We can gather information about how they behave and what they're like and measure them, but we can't necessarily look at them. So if we're going to get information, we got to run these experiments. So based on all this information that we now have, the very first model of an atom was come up with, and it was called the plum pudding model, and it was designed by Thomson. Okay? So he said that the electrons in an atom were distributed like plums in a plum pudding. So you might think of it like oatmeal raisin cookie, right? The raisins are distributed all throughout it. They're not located in just one spot, right? So as you go through it, he thought the mass and the charge of an atom was even all the way across. There were electrons spread all throughout, and if you, let's say you walked through it, right, that you had as likely a chance of walking into an electron in one spot as you did in another. Okay? He was saying they're evenly distributed. So, obviously, people want to test this. They want to come up with their own models. So, they start to run tests. And there were these folks named Rutherford, Geiger, and Marsden that ran an experiment. So, Ernest Rutherford and his associates Hans Geiger and Ernest Marsden, gave us more detail about an atom's structure through this cool experiment that they ran. What they did was they fired alpha particles at a sheet of gold foil. Okay? Alpha particles are positively charged. Okay? So they imagined they should deflect off of negatively charged electrons. Okay? But alpha particles are also 4 times as massive as a hydrogen atom, so they didn't imagine that they would be deflected very much. Okay? Because we know that electrons are negatively charged, but we also know that they do not have a lot of mass. So they expected small angle deflections. Okay? They expected to have these particles go in like it's a plum pudding. Everything's evenly spread out. So when they encounter an electron, they'll deflect a little bit. When they don't encounter an electron, they'll pass straight through. Okay? That's what they were anticipating happening. Okay? But most particles did experience this. Okay? They set up these, basically they put the foil in the center and a thing back at the beginning to fire the alpha particles, and then they put like a screen essentially behind that could detect the alpha particles when they came through. Okay, so some of them passed straight through, and then they saw some deflected to each side, and it seemed like their hypothesis was accurate. Okay, most particles did in fact experience small deflections. However, then they decided to do something that really threw a wrench in their experiment. They decided to check for the possibility that some particles might have had a wide angle deflection. So wide angle would mean that they had returned further back instead of going straight through. Okay? They were looking for a wide angle detection. And they found that 1 in every 8,000 alpha particles had actually been deflected back towards the source of the alpha particles, which would be a huge deflection. So instead of hitting the foil and going off at like a 10-degree angle, it had been bounced back towards the source of these particles. And that did not fit their theory. Okay? At all. They were shocked by this. I believe it's Rutherford who is quoted as saying, it was like you fired a cannon at a sheet of tissue paper and the cannonball came back towards you. That's how shocked they were by this outcome. They were just not expecting it, okay? Because it didn't fit with their current model of what an atom looked like. So, based on this new data, they came up with some hypotheses, okay? So, just checking for your understanding, what did they expect to happen when they fired the alpha particles?
For most just to go straight through.
Right.
And if they did hit the electron, it bounced off the conductor.
Right. They expected most to go straight through, and like you said, some deflect because they hit the electrons. And why did they expect this? Their common sense, right?
Yeah.
Based on what they knew of an atom, this current model of the plum pudding with all the electrons scattered throughout, they expected most of what it's going to come into contact with is just going to barely deflect it. Good. So, they came up with a new hypothesis. Okay? They said there must be a strong force that is occupying a very small volume of space inside this atom. Remember, only 1 in 8,000 alpha particles was reflected. So this wasn't happening every time. So they knew if it wasn't happening every time and it was only happening very, 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 very rarely, that whatever this force was that was sending these particles back had to be occupying a very small amount of space. Otherwise, they would hit it more often, right? Larger target, you'll hit it more often. Tiny target, 1 in 8,000 will hit it. Okay? And then they said that this force must be a densely packed bundle of matter that has a positive charge on it. Because, remember, alpha particles are positively charged. So, they should only be repulsed like that by something that has a positive charge on it. So they said it has to be very dense, occupying a very small amount of space, but because these alpha particles were so massive, they knew it had to have a significant amount of mass, right? And density is your mass divided by your volume, so lots of mass, tiny amount of space, you're having a very high density on this thing. And he gave this area its name. He called it the nucleus. Okay. So we now know that the nucleus is made up of protons and neutrons. And it is a lot of mass in a very small space. So using their tools of the time, they did get a lot of information for us. The nucleus takes up a very small portion of the atom, and where those electrons are, that's a problem that wouldn't be solved for quite some time. Okay, there was a theory, it's called a Bohr's model. It was actually one of Rutherford's students, Bohr, came up with this model later on, and we'll study it later to describe where the electrons are in relation to the nucleus. Because we now know they're not just like mixed in there like plum pudding. Okay, we know there's this nucleus in there that's very densely packed, and the electrons have to be somewhere, but right now they don't know where they are. So they don't really have a great solid understanding of that. They know they're in there, but they don't really have a good idea of where they're at in the end. So, the nucleus. Except for the very simplest type of hydrogen, which only has 1 proton in its nucleus, all other atomic nuclei are made of protons and neutrons. Okay. Protons have an electrically positive charge, and that charge is equal to the charge of an electron, and they have a mass that's 1.673 times 10 to the negative 27th of a kilogram. So, still very small, significantly larger than an electron, right? We go from being negative 31st to negative 27. That's a significant difference in mass. Then we also have neutrons, which are electrically neutral. Neutrons don't have a charge, and they have a mass of 1.675 times 10 to the negative 27. So they are ever so slightly larger than a proton. Usually, positive charges repel each other, right? If you have a positive charge and a positive charge next to each other, they push against each other. So you would think that any nucleus that has more than 1 proton in it would be highly unstable. Makes sense to our logical brain. In actual practice, we find that when protons are that close to each other, they actually exert a force of attraction between them. And the same is true for 2 neutrons that are that close together, and the same is true for a proton and a neutron that are that close together. So what we actually wind up with is what we call nuclear forces. These are proton-proton, proton-neutron, and neutron-neutron forces that are short range, and they hold the nucleus together. So those nuclear forces are just these small forces of attraction, but they're strong between the pieces of a nucleus that help hold it together and keep it from shaking apart. Okay? And this works up until you get a certain number of protons, and then they start to want to escape each other, and that's when we start to get radioactive elements because their nucleus is not stable. And lastly, let's talk about measuring atoms. So for right now, it's easiest to think about electrons moving around the nucleus in what we will call the electron cloud. So think about it as a little cloud that surrounds the nucleus, and that's where the electrons hang out. Okay? When we measure the radius of an atom, we go from the center of the nucleus to the outside edge of this cloud. Okay? So that's our radius, just like the radius of a circle. Okay? Atoms are very, 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 very small, as we've been over. So their radii are really tiny, and we measure them in picometers. Okay? So 1 centimeter is the same proportion of 10,000 kilometers as 1 picometer is of a centimeter. So if you think about how small a centimeter is compared to 10,000 kilometers, that's how small a picometer is compared to a centimeter.
Oh my gosh.
Yeah. So these things are tiny. They're super duper duper small. And if we're thinking about the size of the nucleus compared to the size of the atom, if the nucleus of an atom was the size of a marble, then the electron cloud of that atom would be roughly the size of a football field. So that's how small the nucleus is compared to the rest of the atom. So those protons and neutrons are taking up a tiny amount of space.
Is the electron cloud not within the nucleus?
No, it's around the outside of it.
Okay.
Yep. So atomic radii range in size from 40 picometers to 270 picometers. So they're very, very small guys.